Welcome to MRL. In this today's discussion or learning session will be, this is the second part of the real numbers of CBSE syllabus. In this learning session we'll be learning some important concepts which are covered in 10th CBSE syllabus. Now the first point of discussion is lemma. Now what is a lemma? Lemma is a proven statement used for proving another statement. Please understand this very carefully. Lemma is a statement first of all, and that statement is already proven, and that statement is used for proving another or other statements. That is what is a lemma. Algorithm. An algorithm is a series of well-defined steps which gives a procedure for solving a particular type of problem. So if we have a problem, we have to follow a procedure, and that procedure has certain well-defined steps, and that is what is called as an algorithm. So Euclid's division lemma. This is a lemma which was given by Euclid, and it is called as Euclid's division lemma. It states that given a positive integer, given positive integers a and b, so a and b are positive integers, there exist unique integers q and r satisfying the relation a is equal to bq plus r, where r is greater than or equal to 0 but less than b. Again I'll repeat. The Euclid's division lemma states that given positive integers a and b, there exist unique integers q and r satisfying the relation a is equal to bq plus r, where r is equal to or greater than 0 but less than b. So this is Euclid's division lemma. The meaning is, if there are two integers a and b, there exist integers q and r which are unique and satisfy the relation a is equal to bq plus r. We'll understand what is this relation bit later. Now let us apply this lemma for two numbers 17 and 6. See, a and b are two integers. I have taken two integers here, 17 and 6. So let us apply the Euclid's division lemma to this. Now a is 17, b is 6. Applying Euclid's division lemma, a is equal to bq plus r, we get 17 is equal to 6 into 2. 6 into 2 is 12. 12 plus 5 is 17. So therefore we have here q as 2 and r as 5, which are unique and satisfy the relation a is equal to bq plus r. So therefore it satisfies the relation a is equal to bq plus r and also the conditions of the lemma. So please remember that. Now let us take one more example. Write Euclid's division lemma when a and b are 5 and 12. So we have 5 is a here. 5 is equal to 12 into 0 is 0, plus 5 is 5. Therefore we have here q is 0 and r is 5. And here 20 and 4, 20 is equal to 4 into 5, 4 into 5 is 20, and this is 0. So we have again Euclid's division lemma. So this is how we express Euclid's division lemma, which obeys the relation a is equal to bq plus r and also the conditions of Euclid's division lemma. Now comparing Euclid's division lemma with long division process. We know what is a long division process, or what is the algorithm of long division. The algorithm of long division is very clear, that if you have a dividend, if you divide it by a divisor, we get a quotient and the remainder, and the dividend is equal to divisor into quotient plus remainder, is a long division process of numbers, and the relation is known as the division algorithm. On comparison with Euclid's division lemma, we have the dividend as a, so a is the dividend here, and the divisor is b is the divisor here, and q is the quotient here, and r is the remainder. Therefore Euclid's division lemma is nothing but the algorithm, or a division algorithm, or a long division method of dividing the numbers. Now Euclid's division algorithm, this is very important for us to understand here. It is a step-by-step procedure to find the HCF of any two given positive integers. Already we know what is an algorithm. Algorithm is a procedure which gives a step-by-step method or to find out or to solve a problem. Therefore here we are using Euclid's division algorithm. And why do we call this as Euclid's division algorithm? Because it is an algorithm where we are using Euclid's division lemma, and therefore that is called as Euclid's division algorithm. And Euclid's division algorithm is used to find out it is used to find out HCF of any two given positive integers, and it is a technique based on Euclid division lemma. The Euclid division algorithm procedure is followed, and the procedure is to obtain the HCM of two positive integers, say C and D, that means where C is greater than D, follow the steps given below. That means apply the Euclid division lemma to C and D, that is C is equal to DQ plus R. If R is equal to 0, then D is the HCF. But if R is not equal to 0, then apply again the Euclid's division lemma for D and R, and continue applying the Euclid division lemma until you get R is equal to 0. Then the divisor will be the HCF as soon as R becomes 0. So to understand this, let us take an example and to find the HCF of 455 and 42. Now to find the HCF, apply the Euclid division lemma repeatedly for 455 and 42. Now here 455 is greater than 42, so A is 455, B is 42. Applying Euclid's division lemma, that is A is equal to BQ plus R, we get 455 is equal to 42 into 10 plus 35. Here R is not equal to 0, therefore apply again the second time the Euclid division lemma, that is taking 42 as the dividend and 35 as the divisor. So 42 is equal to 35 into 1 plus 7. Again R is not equal to 0, 7 is not 0, R is not equal to 0. Again apply the Euclid division lemma the third time, taking 35 as the divisor and 7 as the dividend. 35 is equal to 7 into 5 plus 0. So 0 here, remainder becomes 0. Therefore 7, that is the previous, that is the divisor, becomes what is called as the HCF. So for HCF of 455, 42 is 7. So this is a method of finding HCF which is called as the long division method of finding HCF. So what you do, divide 455 by 42, we get 10 as the quotient and 35 is the remainder. Now 35, again, since the remainder is not 0, again divide 42 by 35, we get 1, that is 7 is the remainder, but again 7 is not 0, therefore divide by 5, we get the remainder as 0 here, and the previous divisor is the HCF. This is exactly the method what is followed here in Euclid division algorithm to find the HCF. Then don't forget this. Please learn this method by applying for different groups of numbers, two numbers. Now relation between HCF and LCM. Let us say we have two numbers A and B, and let us understand the relation between the two numbers A and B, their HCF and LCM. Here A and B are terms or any two numbers. HCF of AB into LCM of AB is equal to A into B. That means the product of two numbers is equal to the product of their HCF and LCM. The product of two numbers is equal to the product of their HCF and LCM. This relation is very useful to find the LCM when their HCF is known. So let us understand this by an example. Now to find the LCM of 96 and 404. To find LCM of 96 and 404, let us first find out its HCF by Euclid division algorithm. So 404 is equal to 96 into 4 plus 20, R is not equal to 0. Apply the second time Euclid division lemma the second time. So 96 becomes the dividend here, 20 becomes the divisor. 96 is equal to 20 into 4 plus 16, again R is not equal to 0. Take 20 as the dividend, 16 as the divisor. 20 is equal to 16 into 1 plus 4, that is R is not equal to 0. Again take 16 as the dividend and 4 as the divisor. 16 is equal to 4 into 4 plus 0, R is equal to 0, therefore the HCF is 4. Once we get the HCF as 4, then use the relation that the product of HCF and LCM is equal to the product of the numbers. Use this relation to find LCM. Now HCF of 40496 into LCM of 40496 is equal to 404 into 96, which is the relation which we already know. Use this to find LCM. Therefore LCM of 40496 is equal to 404 into 96 divided by the HCF of 40496, which is 4. When we divide by 4, we get 404 into 24, which is 9696 or 9696. Therefore, the LCM of 40496 is equal to 9696. So that is the procedure of finding the LCM by knowing their HCF. Now, a very important study here, the application of Euclid's division lemma. Now, what are the applications of Euclid's division lemma? We already know that we can use it for finding HCF and LCM, and also to prove general mathematical statements. We have learned how to use it to find HCF and LCM already. Now let us see how we can use Euclid division lemma to prove general mathematical statement. Now let us take one example. Show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is a whole number. Again I'll repeat, show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is a whole number. The meaning is we have to show that every even number is of the form 2q and every odd number is of the form 2q plus 1, where q is a whole number. Now, to prove this by Euclid's division lemma, let us assume the positive integer as a. Let the number be a. Now, since we have to prove it as 2q, let us take b as 2. Then apply Euclid's division lemma, a is equal to bq plus r, then b is 2 here, therefore a is equal to 2q plus r. R is greater than or equal to 0 or but less than 2. Now, if r is less than 2, that means r can be 0 or 1. So, putting r is equal to 0 here, we get a is equal to 2q. And r is equal to 1 is equal to a is equal to 2q plus 1. Therefore, a is even when a is equal to 2q. Please understand, a is even when a is equal to 2q because it is the product of 2 and any whole number, and for any value of q, a is odd when a is equal to 2q plus 1. You can put any value to q here. If q is 1, it is 2, q is 2, it is 4, q is 3, it is 6. That means a is even number. If you take here q as 1, it is 2 into 1 plus 1, that is 3. Therefore, any value of q gives us odd number. So, any positive even integer is of the form 2q and any positive odd integer of the form 2q plus 1, which we have proved using Euclid's division lemma. Now, let us proceed further. Show that, another example here, show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Let the positive odd integer be equal to a. Let us assume that a is a positive odd integer. Now, since we have to prove it as 4q plus 1, I have taken b as equal to 4. By Euclid's division lemma, we have a is equal to bq plus r, or a is equal to 4b is 4 here, 4q plus r. Now, since r is less than 4 but greater than 0 and 1, so r can be 0, 1, 2, 3. So, putting r is equal to 0, we get a is equal to 4q. R is equal to 1, 4q plus 1, R is equal to 2, 4q plus 2, R is equal to 3, 4q plus 3. Now, if you observe very carefully, A is equal to 4q is even for any q, 4q plus 1 is odd for any q, is even for any q, and is odd for any q. Therefore, A is equal to 4q plus 1 or A is equal to 4q plus 3. That means they are odd for any value of q, which is what we had to prove, that 4q plus 1 and 4q plus 3 represent odd numbers for any value of q. So, conclusion is any positive odd integer is of the form 4q plus 1 or 4q plus 3, because when q is 1, 4q plus 1 is 5, when q is 2, 4q plus 3 is 11, and so on. So, that means we have proved that 4q plus 1 or 4q plus 3 represent odd numbers for any value of q, which is an integer. Now, one more example. Prove that if x and y are odd positive integers, please understand, prove that if x and y are odd positive integers, then x square plus y square is even but not divisible by 4. A very interesting question. So, let us again we have to use the Euclid's division lemma here. A is equal to bq plus r is Euclid's division lemma. Let b be equal to 2. Let b be equal to 2, then a is equal to 2q plus r. Since r is less than 2, r can be 0 and 1. So, if r is equal to 0, then a is equal to 2q. If r is equal to 1, then a is equal to 2q plus 1. A is equal to 2q as an even number, 2q plus 1 is an odd number. Now, let us assume that a is equal to 2q is an even number, 2q plus 1 is odd number. Now, here we want two odd positive integers, therefore, I have taken x as 2m plus 1 and y as 2n plus 1. Now, I want a x square plus y square, so I have taken x square plus y square here. X square is 2m plus 1 whole raised to square and y square is 2n plus 1 whole raised to square. Simplifying that and rearranging, we get 4 in the bracket m square plus n square plus m plus n plus 2, and replacing this whole m square plus n square plus m plus 1 by any integer q, then I get 4q plus 2. And if you observe here, x square plus y square is equal to 4q plus 2. Again, it is an even number. So, that means x square plus y square is an even number, but there is a remainder here too. Therefore, x square plus y square is not divisible by 4. So when x square plus y square is divided by 4, it leaves the remainder 2. Therefore, x square plus y square is not divisible by 4. So by this method, using Euclid's division lemma, we have proved that if x and y are all positive integers, then x square plus y square is even but not divisible by 4. So this is the procedure. Using Euclid's division lemma, we can prove any of the mathematical statements given to us. So please remember this application of Euclid division lemma and Euclid division algorithm, a very important study for CBSE real numbers chapter. So understand the basics very clearly, and please go through this, read and listen to what I have spoken to you repeatedly, and scribble them in a book so it becomes a reference for your future reading and understanding the subject. Okay, thank you.